So this is chapter 1, systems of linear equations in two variables, and I'm going to skip the inequalities. So here we have a couple of equations with two variables, x and y, and then we have 6 coefficients. They call them a, b, c, d, e, and f. And here is an example. So they say, okay, elimination method to solve a system of equations. There is another method which is called the substitution method. They do a little bit of it in the next section. In any case, so here they are, and then they're going to go ahead and solve that one here. I'm actually going to look at the example in a moment. And by the way, as we talk about systems of equations, soon we're going to talk about matrices, and we're only going to write the coefficients, such as 1, 1, 30, 3, 8, 180, and it's so much more slick to solve the matrix rather than the system of equations, even though the two are exactly the same. All right, so before we actually go to example 1, nature of solutions. So they're saying, okay, we got these two equations here. They're in x and y, and they're linear, which means these are lines. So these lines, they could be some line here and some line there that are crossing. By the way, I don't like this particular example right here because it looks like the two are perpendicular. They don't have to be. They could be any angle and still cross. And that one right here is the solution that we're looking for. Now, sometimes it happens that these two lines are parallel, at which point they don't cross, we have no solution. And sometimes the two lines are identical, and we have infinitely many solutions. That's called a dependent system, which is what they list here. And we will see that in the example. So there we go, solving system of linear equations. And I just know ahead of time that this one here will have a solution. So we're going to look at it. And by the way, this is highlighted right here because I copied it into Symbolab. We'll look at that also in a minute. So to solve the system, they figure, okay, we got a negative 3x here and a 5x here. Let's try to get rid of one or the other. And we multiply the first one by 5 and the other one by 3, which is exactly what they do here. And they come up with negative 15x and 15x. And the idea is that when we add the two, we have no x's left. Of course, what we did with the 5 times in the first equation, we also had to do that with the y and the negative 5. That's why we get 10y and negative 25 over here. And with the 3 here in the second equation, 12 and 36. If you hear someone in the background, that is my 12-year-old who is apparently really excited playing his video games, and it makes it a little bit harder for me to focus. So in any case, negative 15x plus 15x is the 0 here. We add these two, 22y. We add these two here, 11. Divide by 22, which means y equals 1 over 2, which is one of the solutions. Take the 1 over 2 as a solution for y, plug it into one of the original equations and figure out what the x is, which is exactly what they do here. It takes them a little bit longer. I would actually write it beneath each other instead of one line, but they wanted to save some space, I guess. And they get the solution x equals 2, y equals 1/2. Now, I copied these two equations. That's why they're highlighted into Symbolab, and it was really slick. So here they are. I Googled Symbolab systems of equations, and that's where it got me to. And the thing is, they solved it by substitution. So they're solving one of them for x, plug it in to the other equation, and then figure out what the y is. And then again, there's the 1/2, and they plug it back in, and there's the other solution, the x equals 2, and that's the point. That's the one where the lines would cross. So they actually are I just noticed it, solved by substitution. So let me click, nice, solved by elimination. So there we go. Here, oh, look at that. They do it exactly like they do it in the book, right? Negative 15x, multiply this by 5, multiply this by 3, and then do the other one over here. All right, and then they come up obviously with the same solution, 1/2 and 2. Okay, one more, which is obviously Desmos, right? So I plug them in, and here they are, straight from the book. And then I graph them over here. So I think we can definitely see that this is not perpendicular. So again, like I said earlier, they don't have to be perpendicular. That's why that drawing is a little bit misleading. They could be at angle as long as they cross. And here, of course, is where they cross. And in fact, they identify that point as 2 and 1/2 in the graphical method. All right, let's go ahead with the Part B of the example, this should be a little bit different. So here to solve the system, they figure, okay, we have a negative 2x here and a 4x. Just multiply the first one over 2, which is what they do right here. So they're going to get this one here, multiply everything by 2. Here's still the second equation. They add everything, and notice the interesting thing is everything goes away. 0 equals 0. By the way, if they had 3 equals 3, would be the exact same thing. So 0 equals 0, what does it mean? Well, it means that 0 equals 0 or 3 equals 3. So it means that, hey, that's a true statement. That's fine. But the thing is, what they say down here, it actually doesn't give us any useful information. It is true, but gives us no useful information. So the only one that gives us information now is actually this one right here, negative 2x plus y equals 4. But we can choose whatever x we want and come up with a certain y. And then we choose another x. We come up with a different y, and so on. So how does it look in Desmos? Well, you will see in a moment, those will be two parallel lines. So I'm going to plug in there negative 4x plus 2y equals 8. Give me a moment. So I did this one here. I plugged in the two equations, but I'm only graphing one of them now, okay? So here's the first one, here's the second one, but I'm only graphing the first one, and I get this straight line here. Well, when I click on the other one, let me actually make this a little bit bigger here, right? Like this. Click on the other one, there it is, it's right on top. If I turn the green one off, there's the purple one. Turn the purple one off, turn the green back on, turn the purple one on, and there you go. One and the same one, which means we have a dependent system. We have infinitely many solutions, which is then what they say right here. That is actually all the solutions that we have, or they can express it like this. All right, and the third one here, part C. So to solve this system, they again do, okay, let's multiply the first one by negative 3, because then we're going to come up with 6x and minus 6x from the second equation. And then let's see what happens to the other stuff. Everything would have to be multiplied by negative 3 in the first equation. There we go. Add it here, and then we're going to come up with 0 equals negative 2. What does that mean? Well, that's obviously false. So what happened here? Well, it's false, so something is wrong here. And the thing that's wrong here is that there are no solutions, which is what they're saying in this sentence down here. Second equation is false. The system of equations is inconsistent and has no solution. Let's see what happens when we graph that. So 6x minus 3y equals negative 12. Be right back. All right, so here I have the two equations. I didn't turn them on yet. So here's the first one. There you go, that line there. And I'm going to turn the second one on, and notice the two are parallel to each other. Well, obviously they're never going to cross, and therefore there is no intersection ever, so there is no solution. And that's what that means, that we came up with this false statement, which implies no solution. And that's what I wanted to show for this section.